Hello everyone, in this video we are going to talk about electric flux and the Gauss's law. And for you to understand what is Gauss's law, we need first to know what is an electric flux and how to calculate it. The word flux means flow, and electric flux means the rate of flow of an electric field through a given surface, and it also means the amount of electric field penetrating the surface. This means that the larger the area, the more electric field lines passes through it. And the stronger the electric field, the greater the electric flux. And electric flux is denoted by the symbol phi with a subscript E. This means that electric flux is directly proportional to the electric field and to the area of the surface. So mathematically, we can write the formula of an electric flux as the dot product of the electric field and the area. We can also rewrite this formula as electric flux is equal to E times A cosine phi, where this symbol means electric flux and E stands for electric field and A is the area of the surface, and of course the angle phi is the angle between the electric field and the normal line. So this is now the formula of electric flux. Now let us understand more electric flux using diagrams. Imagine that we have a surface. Let's locate first the normal line. And the normal line is a line that is perpendicular to the surface. So in this figure or in this surface, here is the normal line. And this is perpendicular to the surface. Let's say that there is an electric field that passes through it. As you can see, the electric field lines or the red lines is parallel to the normal lines or to the broken lines. So the angle phi now here will be 0, since the angle phi is the angle between the electric field and the normal line. So this also means that the electric field is perpendicular to the surface. So the electric flux for this situation will be equal to E times A cosine phi, wherein we can simplify this as cosine 0, and cosine 0 is equal to 1, thus the electric flux for this one is EA. So this is all true to all surface with electric field that passes perpendicularly to the surface or with parallel to the normal line. And we get the maximum electric flux. What happens when we tilt this surface? So for example, we have tilted the surface or this way. Now let's locate again the normal line. And again, the normal line is the line that is perpendicular to the surface. So meaning, if this is the surface, the line that is perpendicular to it is the normal line. So here is the normal line or the broken lines. Now if we did not change the orientation of the electric field that passes through it, let's draw it again. So we have electric fields. Now let's locate the angle phi or the angle between the electric field lines and the normal line. So here will be the angle phi. So in this case, the electric flux will be E times A cosine phi. And suppose that the angle phi is equal to 60 degrees. So we can have the electric flux as E times A cosine 60. And by using your calculator, you can easily solve for the electric flux. Now, what about if we change again the orientation of this surface? So let's say that we have this surface this way. So let's locate again the normal line. Again, the normal line is a line that is perpendicular to the surface. So here is the surface, and a line that is perpendicular to it is the normal line. So the broken line here is the normal line. So again, let's not change the orientation of the electric field. So let me draw again the electric field lines. So as you can see, let's identify again the angle phi. And the angle phi again is the angle between the electric field and the normal line. So as you can see, the electric field and the normal line forms a 90 degree, or they are perpendicular to each other. So meaning the angle phi will be 90 degrees. And the theta, or the angle between the electric field and the surface, is equal to 0, or the electric field is parallel to the surface. So the electric flux for this one will be E times A cosine phi, wherein our phi is equal to 90 degrees. So evaluating cosine 90, it will give you 0. So meaning the electric flux for this one will be 0. So this means that there are no electric field lines passes through the given surface because they are parallel to the surface. Now let's have a sample problem for electric flux. So let's have this problem. A uniform electric field E is equal to 8,000 newtons per coulomb is passing through a flat surface area of 10 meters squared. Determine the electric flux. So the first thing that we need to do is to identify the given. So the given in this problem are the electric field, which is 8,000 newtons per coulomb, and we also have the area, which is 10 meters squared. So the angle phi is not given because the problem means that the electric field is parallel to the normal or perpendicular to the surface. So the angle here would be 0. So now let's have the equation or formula. The formula for electric flux is E times A cosine theta. And for the solution, it is very simple since we only need to substitute the given to our formula. So electric flux is equal to 8,000 newtons per coulomb times 10 meters squared cosine 0. So we have 8,000 newtons per coulomb times 10 meters squared times, since cosine 0 is equal to 1, so this means that we only need to multiply 8,000 times 10. That gives us the answer of 80,000 Newton meter squared per coulomb squared. So this is now our electric flux. Or it is only in coulombs. So our final answer would be 80,000 Newton meter squared per coulomb. Let us have this problem. Calculate the electric flux through a rectangle of side 1 meter and 2 meter kept in a region of uniform electric field of 5,000 newtons per coulomb. The angle of the electric field to the normal is 60 degrees. Now, for you to understand better the problem, let's draw the electric field and the surface. So we have a rectangular surface which has a dimension of 1 meter by 2 meters. So for example, this is the normal line, and the orientation of the electric field to the normal is 60 degrees. So let's say that we have the electric fields oriented this way. So the angle phi is equal to 60 degrees. So let's calculate the electric flux, but first let's identify the given. So we have the dimension of a rectangle, and the area for a rectangle is length times width. Thus we have 2 meters times 1 meter is equal to 2 meters squared, and this is now the area of our rectangle. And for our electric field, it's already given, which is 5,000 newtons per coulomb, and the angle phi is 60 degrees. Now let's solve for the electric flux. Electric flux is again E times A cosine phi. So let's substitute the given to our formula. 5,000 newtons per coulomb times the area, which is 2 meters squared, times cosine 60 degrees. And cosine 60 degrees is equal to 1/2. Thus we have 10,000 newtons or newton meter squared per coulomb divided by 2. We will have an electric flux of 5,000 newton meter squared per coulomb. So as simple as that. Now let's try to find the electric flux in an enclosed surface. Suppose that we have a sphere, and at the center of the sphere is a positive charge. We all know that the positive charge have electric field lines that points outward, and these electric field lines form 90 degrees with the surface, or they are perpendicular with the surface. This means that the angle phi will be always equal to 0 at any point of the surface of the sphere, and cosine 0 is equal to 1. Thus the electric flux for this one is only E times A. And the area of the sphere is equivalent to 4 pi r squared. So the radius of this one is here. In our previous topic, we also discussed the formula of electric field as Q all over r squared. And K, which is a constant, can be actually solved by 1 all over 4 pi epsilon naught. So we can substitute these formulas into our main formula, which is E times A. So our electric flux will now become electric field times the area, which is 4 pi r squared, and the electric field is equivalent to KQ all over r squared times 4 pi r squared, and K is equivalent to 1 all over 4 pi epsilon naught times Q all over r squared times 4 pi r squared. So we can actually cancel the same units or the same values. So we would have 4 pi r squared cancel. We also cancel this one and cancel this one. Thus, our remaining formula will be Q all over epsilon naught. And this is actually the statement of the Gauss's law, wherein the total electric flux through a closed surface is equal to the net electric charge inside the surface divided by epsilon naught, wherein epsilon naught is equal to 8.85 times 10 raised to negative 12 Coulomb squared per Newton meter squared. So I hope that you understand the concept of the Gauss's law and electric field. So this formula applies to all type of enclosed surface, whether it is a cube, a rectangular prism, a cylinder, or a sphere, as long as the electric charge or the source of the electric field is inside this surface. Now let's have an example. Suppose that we have an electric charge with a charge of 5 microcoulomb, and this is enclosed in a sphere. Calculate the electric flux. So we have the formula for electric flux using the concept of the Gauss's law as Q enclosed divided by epsilon naught, because according to Gauss's law, the total electric flux of an electric field that is enclosed in a surface is equivalent to the charge divided by epsilon naught. So our Q here is 5 microcoulomb, or this is also equivalent to 5 times 10 raised to negative 6 coulomb, and the value of epsilon naught is equivalent to 8.85 times 10 raised to negative 12 Coulomb squared per Newton meter squared. Now we can now substitute the values into our formula. Our Q enclosed is 5 times 10 raised to negative 6 coulomb divided by 8.85 times 10 raised to negative 12 Coulomb squared per Newton meter squared. And 5 times 10 raised to negative 6 divided by 8.85 times 10 raised to negative 12 would give you an answer of 564,971.75 Newton meter squared per Coulomb. So this will be now the electric flux of this enclosed charge. As you can see, the area or the surface area of the sphere does not affect its electric flux. Now let's analyze this case. As you can see, we have a rectangular prism, which is obviously an enclosed surface. What if the source of the electric field is not inside this closed surface? So suppose that we have an electric field that passes through it, and this comes from left going to right. So the electric field at the left side will be negative, thus the electric flux is negative EA. And for this one, the electric flux will be positive, thus we have positive EA. Now, if we get the net electric flux of this one, these two will cancel each other because what goes in will go out. Thus, the net electric flux for this one will be 0. So, in an enclosed figure, for example a rectangular prism, in this case, the total electric flux will be 0. For example, we have a cube. With a positive charge inside it. We can actually solve using the Gauss's law, its electric flux is, since this is an enclosed figure, so the electric flux will be Q all over epsilon naught. So after solving this one, you can actually divide it by 6 to get the electric flux on each side, since we have 6 sides of a cube or a rectangular prism. In that case, you will get the electric flux for each side. But if you want to get the electric flux using the Gauss's law of this enclosed figure, this will be the formula. And if you want to get the electric flux of each side, for example, this side or this side, another side, and the back side and the front side, you will have this formula since we have 6 sides of a prism. So that ends our discussion about electric flux and Gauss's law. So I hope that you have learned something, and please answer the problems that I gave you and follow the directions. I have actually included a statement below the problem, so please follow that. And goodbye. Thank you for listening.